Static characteristics of measurement systems, and this presentation is rather large, so I split it into 3 films. And again, if you have questions, please contact me on matthias@bota.no. And let's see what static characteristics, what they are. Well, you have here static characteristics. They are the characteristics of an instrument, especially when we talk about measurement systems. But what you have in static is that it's when the value has settled. So this is the static response of the instruments. So let's say that I put myself on a bathroom scale, for example, and the needle would go up and then swing below and then finally settle on a stable value, and that is when I read the data from the bathroom scale. Before that, there's no point in me reading the data, so I step onto the bathroom scale and then I wait for like 2-3 seconds and then I read the data. So what we're going to talk about today is the static response, not what happens here. This is called the dynamic response. That is when you get an equation for the time varying properties of the signal. So it's a set of criteria defined for an instrument. So we have defined the criteria for the instrument, like what kind of output do we get to a certain input. And these are quantities that are slowly varying with time or mostly constant. You might have something that slowly varies with time. For example, let's do the bathroom scale again. Let's say that I step onto the bathroom scale and it shows how much weight I have, the mass of my body. And let's say that I stand there for like a day or something, then I guess that the needle would slowly go up actually as the spring gets more and more worn out. You may have slow changes, but not fast changes like that. That this one will settle within a 2 or 3 seconds in the bathroom scale example. We have to define a few properties, and one of them is range. In Norwegian, that would be område. And it's specified by the minimal and maximal values, and also span, which is the difference between minimum and maximum. So here, for example, for this temperature meter, I would have a range that goes from 500 to 2500 degrees. So the range is from 2, and the span is 2000 degrees. That's the delta between the max and the minimum. For every instrument, we can define something called the ideal straight line. That would be if there was a straight line dependency between the input and the output, like here. Let's say that this is the input and that is the output, and that would be the input span here. It looks like this figure is stolen from a Spanish one, going pressure on the input axis and output current on the output axis. So the input span would be from 500 to 3000, I don't know what, maybe PSIs, and the output would be from 4 to 20 milliamps. And the relation here is a straight line between the two. So we have here a straight line dependency, the ideal straight line. So the output is some constant multiplied by the input and then with a bias A added. So the constant K defines the slope of this line here. A larger K would mean a steeper rise to the graph here. and a higher A bias, that is actually the zero input, the output at zero input. So if we take this line here and extends it a bit, I guess it would land about here. So that is where you find your A. The crossing point here between the zero input and the y-axis, that is the value of A. So if A increases, the whole line here would lift upwards in parallel. It would be parallel ported upwards. So another word for K is the sensitivity. The steeper the graph here, the more sensitive instrument. A small change to the input would give a large change to the output for a more sensitive instrument. Output span over input span. That is how we calculate the K. O max minus O minimum, I max minus I minimum. And A is the bias which we find when the output is zero. Of course, you may also have non-linear systems. So this line here is the ideal straight line, but most systems are actually a bit non-linear. So you have to take that into consideration as well. Now, so you have the K times I plus A, that is the sensitivity, multiplied by the input plus the bias. That's what we had from the last page here. Then you have some equation for the nonlinearity. And shown here in this graph, the nonlinearity here alone without the Ki plus A term. But if you take that nonlinearity over to this graph, which is the full output graph, you see the nonlinearity adds up to in addition to the straight line. So now you have an equation which also includes the nonlinearity. In many cases, you don't describe the nonlinearity function itself because you don't have it. In some cases you do, but in many cases you don't have it. And if you don't have it, you rather express the maximum nonlinearity. And if you watch closely, you see the maximum nonlinearity would be about here. So the n with a hat on it is the maximum nonlinearity, and it's also without a sign, so it's always the absolute value is positive. So here is where you find the maximum nonlinearity, and you compare that to the output span. Of course, if we have a larger output span and it's the same gap here, well, the gap would be smaller if the scale was all the way up here compared to the full output scale. And if that output was almost flat, you had the same gap between there, then the output, the nonlinearity would be have a stronger effect on the input-output relationship. So you look on the nonlinearity as a percentage of full-scale deflection, FSD. Example for nonlinearities is this instrument here. It's a current transmitter with RTD excitation and linearization, so and it has its linear the nonlinearity here, which is 0.01 what percent. So it's a percent of the full scale of the instrument.